Hi, and welcome back to the Quantum Rings Quantum Summer School. Last week, we learned all about quantum oracles, and this week we're going to put it to use. Today, we're going to be talking about 3 toy algorithms: the Deutsch Jozsa algorithm, Bernstein Vazarani algorithm, and Simon's algorithm. While these algorithms may not perform any useful function, they really illustrate the power of quantum computing, and they show us how quantum superposition and phase interference can help us outperform classical computers. Let's get into it. Today, we're going to be covering 3 toy algorithms. And by toy, I mean that maybe the algorithm doesn't exactly solve a very useful problem, but it's a helpful example and it can kind of illuminate the power that quantum computing has. And in particular, these 3 toy algorithms really leverage both quantum superposition and also phase interference. And we're going to see how that works today. So the first thing I want to talk about is the Deutsch Jozsa algorithm. So the general problem statement here is that we're given some function which goes from the bit strings of length n to 0 or 1. And just remember that this notation just means all the bit strings of length n. And then this is either 0 or 1. And then the goal is to determine if f is constant or balanced. And what do I mean by that? So if f is constant, that means for all inputs, the output is the same. And if it's balanced, then it's 1 for half of the inputs and 0 for the rest. So here would be an example of a constant function because f is always 1. And then here would be an example of a balanced function because for half of the inputs, f of x is 0 and the other half, it's 1. So classically, how would we go about doing this? Well, we don't have a lot of options. Basically, the only thing we can do is evaluate the function. So we'll take a look at one input, and then another input, and then another input, and we can keep checking as many inputs as we want. So in a really lucky case, let's say we met the first input gives us an output of 1, the second one is 1, and then the third one is 0. Okay, great. Then we know that this is a balanced function because a constant function can't have 2 different answers. But here's another problem we could run into, which is what if I get as a result 0, 0, 0, so on and so forth, until I get to the 2 to the n minus 1th input. At that point, it could be the constant 0 function, or I could just be extremely unlucky and the next one is going to be 1, and the rest will all be 1, and it's a balanced function. So actually, in the worst case scenario, we would have to check 2 to the n minus 1 plus 1 of the inputs in order to be sure whether f is constant or balanced. But with quantum mechanics, we can actually use quantum superposition to test all of the bit strings of length n in one query. The first thing we need to do, though, is we need to translate our function f of x into something that our quantum computer can understand. So last week, we learned about oracles, and oracles are a way to encode functions or computations into a set of quantum gates. So basically, we're going to take our function f of x, and we're going to turn it into a quantum oracle. And the way this oracle is going to work is we're going to have some inputs here. This is our bit string x, and then we'll have some auxiliary qubit, which we'll call y, and then at the end of the circuit, it's going to output again x, but then here it's going to be f of x plus y, and this plus here just means addition mod 2. So we can see some examples of this kind of oracle, just to see how we go about constructing it. We talked about this a little last week, but I'll go over it again, because this is really important. So consider this example where we have the constant 0 function. So whether x is 0 or 1, f is always 1. And then we can consider the case of y being 0 or 1 in either of those cases. So first, let's just figure out what f of x plus y is. So for the first one, 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. Okay, So basically what we're seeing here is that whatever the value of y is, it's flipped at the output. So we can describe this unitary as just an x gate on the bottom qubit. Okay, now what about a balanced case? So now consider that f of 0 is 0 and f of 1 is 1. Now in this case, we're going to have f of x plus y being 0, 1, 1, 0. And now we can see that when f of x is 0, which is when x equals 0, y stays the same. But when x is 1, y gets flipped. What gate is this? Yeah, this is our C0 gate. So we'll get a bit flip on y, conditional on x being in the 1 state. So that brings us to the full algorithm. The first thing that we're going to want to do is apply a Hadamard gate to all of the qubits. That's going to put us in an equal superposition of all the bit strings of length n. Then we're going to apply our oracle, and then finally we're going to apply Hadamards to everything again to undo the superposition, and then finally we're going to measure. So let's walk through this circuit step by step at all of these points 1, 2, 3, and 4 that I've marked, and look at what the state of the circuit is at that point. So at the start, we have all the qubits in x in the 0 state and the qubit y in the 1 state because we applied an x gate to it. So our overall state is just 0 n times and then 1 for the qubit y. Then we're going to apply a Hadamard gate to all the qubits. And we know the action of the Hadamard gate. So the Hadamard gate acting on the 1 state gives us minus, and acting on the 0 state gives us plus. But actually, we also know that when we apply Hadamard gate to the all 0 state, we get all the bit strings of length n. So we can express this as 1 over root 2 to the n times the sum of all bit strings of length n, that bit string, and then the minus state. Now at this third point in the circuit, we've applied the unitary. So let's take a look at that. So we have our same thing from before, but now we have our unitary acting on x and minus. And I can bring this unitary inside the sum because all of this is linear. So you can just distribute the unitary inside. So now we can just apply the action of the unitary, which we can do because we can break this up into something a little bit easier. So this is, recall, 1 over root 2, 0 minus 1. And the action of the unitary is as follows. Pick up an extra root 2. So we're going to get f of x plus 0, which is just f of x. And then we're going to get minus f of x plus 1. So now we want to figure out a better way to express this. And what we're going to do is actually called a phase kickback. And what that means is right now we have this expressed with the f of x as part of the qubit y, but we can equivalently re-express this with the phase in front of the x part of the system, the x register. So what I'm going to argue is that 1 over root 2 f of x minus f of x plus 1 is actually equal to minus 1 to the f of x times minus. And we can pretty easily check this because there's only two possible values of f of x. So if f of x equals 0, then we would have 1 over root 2, 0 minus 0 plus 1 is 1. And this is just equal to minus, and this is in fact minus 1 to the f of x minus. And when f of x equals 1, we'll have 1 over root 2, 1 minus 1 plus 1 is 0. And this is equal to minus minus, which is minus 1 to the f of x minus. Okay, so now applying our phase kickback, we can rewrite our state as 1 over root 2 to the n, sum over x, minus 1 to the f of x, x minus. The final step is to apply Hadamard gate to all the qubits in register x. And now the question is, what is this quantity here? All the Hadamards applied to some arbitrary bit string x. Well, let's just give one example of this. So consider 3 Hadamards applied to the bit string 0, 0, 1. We can write this out. We get like 1 over root 2 to the 3 times 0 plus 1 times 0 plus 1 times 0 plus 1. And if we FOIL that out, we're going to get 1 over root 2 to the 3 times 0, 0, 0 minus 0, 0, 1 plus 0, 1, 0 minus 0, 1, 1 plus 1, 0, 0 minus 1, 0, 1 plus 1, 1, 0 minus 1, 1, 1. One thing that we can see from this is that there's a minus sign out in front if and only if the dot product of 0, 0, 1 with the bit string is 1, and otherwise it's 0. So basically there will be a minus sign if x dot z equals 1, where this is x and one of these is z. So now we can express our Hadamard gate a little more clearly. This was the last step that we needed, and now we can put it all together and find our final state at the end of the circuit right before measurement. So this was going to be 1 over 2 to the n, sum over x, sum over z, minus 1 to the f of x, plus x dot z, z minus. This may not look particularly useful, but we only have to think about the amplitude of a particular state. So what is the probability of measuring the all zero state, which is when z is just the string 0, 0, 0, etc. So the amplitude of this state is going to be given by it's going to be proportional to this. But z is 0, so this term is going to vanish. And then we just have the sum over all the inputs, and then minus 1 raised to f of x. So if f is constant, then either f of x is always 0 or f of x is always 1. And that those minus 1s and 1s are going to add up constructively. So we'll either end up with 2 to the n copies of minus 1 or 2 to the n copies of 1. So with that, we're going to get that the probability of measuring that state is 1. On the other hand, if f is balanced, then exactly half are going to be 1 and exactly half are going to be 0. So we're going to have the same number of 1s and minus 1s in that sum. They're all going to cancel out, and the probability of measuring that state is going to be 0. So now we've reached our conclusion, which is after we do this whole circuit and we measure the x register, if we measure the 0 state, it's a constant function. If we measure anything other than the 0 state, it's a balanced function. So what this tells us is that we can determine whether it's constant or balanced in one query, and this is regardless of n. So this is a pretty cool result and like a very, very dramatic speed up compared to the classical best approach. You may ask, okay, well, this doesn't seem particularly useful, and that's true. It isn't particularly useful, but it does illustrate some of the power that quantum mechanics has. So the reason that this was able to work was, one, because we were able to use quantum superposition to basically send in a superposition of all the bit strings of length n at once. And then at the end, we were using that phase kickback and then the either complete constructive interference or complete destructive interference of the phases in order to know what the function was from our measurement result. Okay, so now let's move over to the coding notebook. First, import all the libraries that we need, and then there's also some helper functions here. The first thing I want to do is practice making some oracles. So the first one that we might want is the constant 0 oracle. And for this one, we know that f of x is going to be 0, so f of x plus y is always just y. So we don't want anything to happen to qubit y, so we should just let it pass through. So for the constant 0 oracle, we would do nothing. And now we can see what would happen in all possible scenarios. So the possible inputs for x are 0, 0, 0, 1, 1, 0, and 1, 1, but for each of those, y could be 0 or it could be 1. And so we can check out the result, which is whatever y is, f plus y is the same thing. So this is indeed our constant 0 function. What about the constant 1 function? F of x is always 1, so f of x plus y is always flipping y. So if y was 0, it will become 1. If y was 1, it should become 0. So for this one, we want to apply an x gate to our qubit y. And now we can see that f plus y is always flipping y. Now, if we want to make a balanced oracle, then in order to do that, we need whether or not y is flipped to depend on x. And so we can do that with a controlled NOT gate, like how we just saw. So there's lots of ways that we can do this, but one way is we could just apply a C0 controlled on the 0th qubit of x, targeting qubit y. Oops, that was a typo. Okay, so now we can see that for some of the inputs, f plus y is the same as y, but then for some of them it's flipped. So for instance, this one is flipped. So this is indeed a balanced function. So now we can put together the full algorithm. So we can define our oracle where we can choose whether f is constant 0, constant 1, or balanced. So for these, we can just put in the same ones that we did before. So for constant 0, we could just do nothing. For constant 1, we can just apply an x gate on qubit y. And then for balanced, we can use a C0. And now we can put this together into a full algorithm. So let's remember the pieces. So the first thing that we want to do is put everything into an equal superposition. So we're going to apply Hadamard to everything in register X. And then we also want to prep Y in the minus state. So we can do that with an X gate and then a Hadamard. Then we want to apply our oracle. So we have our oracle, and we can choose our X. So maybe first let's just do the constant 0, 1. And then finally, we need to undo the superposition. And I'm not saying that this is necessarily going to put us into a certain bit string state, but happens a lot in algorithms where we do something initially and then at the end we undo it. And then there will only be a change if there's something conditional that happened that altered something in the middle. So here's our Deutsch Jozsa algorithm with a constant 0 function, and we can run this 1,000 times. And we measured the all 0 state. So that's a good indication based on what we talked before that this is a constant function. And we can also check for the constant 1 function. We also measure 0, 0 every single time. We can also try our balanced function here. And now we measured something different. With the balanced function, there's a 0% chance of measuring 0, 0. So we'll measure something else for sure. But measuring not 0, 0 tells us we have a balanced function. So I would encourage you to play around with this. Especially, you can make the registers bigger, have more qubits, try and build up larger oracles that involve more qubits. And you can verify for yourself that this still holds true. Constant F, all 0 state. Balanced F, never the 0 state. That brings us to our next algorithm, which is the Bernstein Vazarani algorithm. And in this algorithm, we have some mystery bit string S. And then we're given a function F, which goes from the bit strings of length n to 0 or 1, and that performs the dot product of X with S mod 2. So for this, I mean, for example, if you had 0, 0, 1 dotted with 1, 0, 1, you just go pairwise through the elements. So the first 2 elements here would be like 0 and 1. So 0 times 1 is 0, plus now the second one, 0 times 0 is 0, and the last one plus 1. So this would be 1. And if it was some number larger than 2, you would just do modulo 2. So let's consider an example of such a function. So consider the state s equals 0, 1, 1. Then f of x is going to perform x dot s, and maybe try this out for yourself first. But the first one is of course going to be 0, and then the second one would be 1, 1, and this is 0 because we end up with 2, modulo 2, and then 0, 1, 1, and 0. And the problem that Bernstein Vazarani algorithm solves is finding s. So you're given this function, find s. So what is our classical approach? Well, we know that s is going to look like this. It's going to be composed of n bits, so s1, s2, all the way to sn. And we can just go through n different bit strings to pick out these elements. So for instance, if we wanted to pick out s1, we would put in the input 1 and then all zeros. Because when you do the dot product, it will just give you s1. You can do the same thing to get s2. And so on until you get all the way to the end. And that gives you sn. So after you've done that, you've completely built up the string s, and you're done. So that took n queries. And if we use a quantum approach instead, it's only going to take one. So let's look at our quantum approach. And if you'll notice, this circuit looks exactly the same as the Deutsch Jozsa circuit. The only difference here is what the unitary UF is. It's going to be different in this case, but you can see that the overall structure is exactly the same. In this case, our unitary is still doing the same thing actually. It's taking in x and y and spitting back out x and f of x plus y. But we have a very special f of x, so we can actually know exactly what this does. So right before we perform the measurement, the register x is in this state. And I'm just grabbing this exactly from the Deutsch Jozsa algorithm that we just walked through because everything up to this point is the same. But now we have more specific information because we know that this is x dot s. So now we can simplify this a little bit. And now again, we can ask ourselves, what is the amplitude of the state s? Well, if z is equal to s, then the coefficient in front of the s state is going to be this. And s plus s is always going to be 0. If you add a binary number to itself, you're going to get 0. And then when we take this coefficient squared, we will just get 1. So the probability of measuring s is 1. Okay, so this is a little bit different of an oracle than before. So this oracle is going to give us x and then x dot s plus y. So how do we make UF? Let's first look at what this looks like. So just writing it out a little bit, we can rewrite x dot s as x1 times s1 plus x2 s2 plus dot 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 xn sn, and this is our y. So now we can see that basically for each one of these that are 1, we're adding 1 to this long sum, and that's essentially corresponding to a bit flip. So every time one of these entries is 1, we're applying another bit flip to the qubit y. So just looking at an example here, if we had s equals 1011, then we just need to apply a controlled x everywhere where s is equal to 1. And that way, if we're in the state s, we'll apply all these controlled knots, and then for other bit strings, it will be some portion of them. So let's go back to the coding notebook now. And let's build up the Bernstein Vazarani oracle together. So the first thing that we'll want to do is, given a string, we want to reverse the string order to match the default ordering in quantum ring / Qiskit. So we can get the inverted string, which will just be this written backwards. And then we want to apply our gates. So for I in range the size of qx, that's just the number of qubits in that register. If that bit is equal to 1, then we want to apply a controlled x gate. And that's going to be controlled on the ith cube and qx, targeting qy. And now we can build up our circuit exactly the same as before. So we got to apply a Hadamard to everything in qx. We have to prep qy in the one state. So first apply an x gate and then a Hadamard gate. Then we're going to apply our oracle. And then finally, we need to apply a Hadamard to everything again. And of course, we need to pick our secret string. So maybe let's just pick 110, but you can pick whichever string strikes your fancy. So here's our circuit. And then I just want to emphasize here the ordering of the bits. So in Qiskit, the least significant bit is index 0, so that would be this one here. And then the most significant bit is the highest index, so that would be this one here. And you can see that's matching up with what we want. And now we can run this 1,000 times. And we get the 110 state, which is what we wanted. So we can also try other states as well. Like maybe I want even 4 qubits. Ta-da! Okay, so feel free to play around with that by yourself. I think it's pretty fun. And then if you want an extra challenge, there's the probabilistic Bernstein Vazarani algorithm, where now instead of 1 secret string, you have 2 secret strings. So there's a problem here that can walk you through how to pull that off. And the last thing I want to talk about today is Simon's algorithm. And Simon's algorithm is the most complex of the toy algorithms that we're talking about today. And it's also one of the algorithms that inspired some of future algorithms which are actually really useful, like Shor's algorithm for factoring numbers into their primes. And Shor's algorithm is a really impactful algorithm in the field of cryptography because RSA key encryption relies on the fact that numbers are really hard to factorize into their primes when they're large. So we're going to learn about Shor's algorithm later on in the course. But first, let's talk about Simon's algorithm. So again, we have a mystery string S, and we're given some function from the bit strings of length n to now not 0 or 1, but also to bit strings of length n. And this function is going to satisfy that f of x equals f and y, f of x equals f of y, if and only if x plus s equals y. And what we want to do is we want to find s. So basically what this means is that this function f of x has some periodicity to it, and that periodicity is s. So I can give you an example of one. So here we can, maybe just looking at this, it's not totally obvious, but we know that they should have the same output if x plus s equals y. So we can look at what has the same output as the 0 state. And we can see that here has the same output, and that's the state 0, 1, 1. And then we can see that actually all of the states that have the same output are off by 0, 1, 1. So here we have like 0, 0, 1 plus 0, 1, 1. That's going to be 0, 1, 0. So those two are a pair that go together. And the same is true for the other outputs as well. So this is just to emphasize for the strings 0, 1, 1. So classically, what can we do? Well, you can just query until you find 2 inputs with the same output. So just keep trying, and then eventually you'll get 2 that have the same output, and you can see what the difference between them is. But there's a little bit of a tricky issue here, which is that if s is equal to 0, then that means that actually every input has a distinct output. So you'd actually have to check half the inputs plus 1 in order to be sure that it's that S is equal to 0 and not something else. So our quantum approach is a little bit different, and the structure of the algorithm looks very similar to the ones that we just talked about, but now instead of just one qubit Y, we have a register of size n as well. And I'm not going to walk through all of the math here. If you're curious, you should definitely look into it more, but the basic principle is the same, where we're using quantum superposition, and then we're getting this phase kickback. And under a certain condition, the phase either completely constructively or completely destructively interferes. And then we can use that to solve our problem. So the end result that we're going to get is that if you have a bit string z, if z.s is non-zero, then the probability of measuring z is 0. So basically what that means is at the end of this circuit, the only measurement results that we're going to get are bit strings that are 0 when dot producted with s. And that gives us a system of equations. So we would have to run the circuit several times. So let's say if n was 3, we would have to keep running the circuit until we get 3 distinct measurement results. And then we would have a system of 3 equations and 3 variables, which is the elements of s that we want to find, and we can solve for s. And then I just want to emphasize the magnitude or the order that these algorithms are. So classically, you have to check basically half of the elements in order to be sure in the worst case scenario. So it's order of 2 to the n over 2. And quantum, on the other hand, you're just trying to find n distinct measurement results. And so this is going to be order n. So now let's hop back over to the notebook. The first thing we want to do is build the Simon oracle. And the Simon oracle is a little bit more complicated than the other ones. But the very first step is just to copy the X register to the Y register. And think about how you might do that. You have n qubits, and you just want to copy their state down to another register. Well, we can use the C0 gate to do this. So we can loop through all the qubits in the register, and then we just use a C0 gate to copy the state of that qubit down to the equivalent one in the Y register. And then we need to apply conditional gates. So the way that Simon's algorithm oracle is going to work is we need to find the place where there's the lowest index bit that's 1 in the string s. So we can just call this the first 1 index. And we can get that from doing this. And then we take that qubit in the X register and we apply controlled NOT gates to everywhere in the Y register where S is non-zero. So again, we're going to loop through the Y register. And then if S is non-zero at that index, then we want to apply a controlled X gate. And this is going to be the first 1 index applied to QY. Okay. And then for Simon, we just have Hadamard's on X before and Hadamard's on X after. So Hadamard's on X. We have our oracle. And then Hadamard's again. And we need to pick our secret string, of course. So let's just have this be 101. Oops, I should include this here too. Oops. It should be a for statement. Okay. So now here's our circuit. We have our Hadamard gates. We have that chain of C naughts copying our state from the X register down to the Y register. And then we have that special part where we're doing controlled X's from that qubit with the first bit that's 1 in the mark string. We can run this 1,000 times. And we got 4 different results here. And the one thing that we know is that these results ought to have a dot product of 0 with our string. So we can actually check that. And we can see that our string 101 dot product with each of these measurement results that we got, it's always 0. So this is good, this is what we wanted. If you want to play around with this more, see what happens if you set S equals 0. So now every input has a distinct output. And then also try putting more qubits in and see the scaling of how many queries you need. So here we're doing 1,000, which is way overkill. Like, how few shots could I do and still get away with knowing what the bit string should be? Today was all about toy algorithms, but next week we're taking it to the next level. We're going to be talking about Grover's search algorithm, which is the first genuinely useful algorithm that we'll learn in this course. And looking ahead, in the next couple of weeks, we're going to be learning about Shor's algorithm, which is inspired by Simon's algorithm, which we learned today. See you next time.